So I posted a reminder that we're going to discuss the exercise
Yeah.
that we agreed, which is the number 5 in that section of the exercises. And if you want, I just can show what is the scope of the exercise, and then if you want, you can start with your solution, and then maybe I can comment or add something to make a point. Okay, so let me share my screen. Okay, can you see my screen?
Yeah.
Okay. All right, so this chapter is about exponential smoothing models. And in this exercise, we're going to practice some of the theory that we discussed in the previous sessions. So in this exercise, we're going to use the global economy data set that is provided in the library on the textbook FPP3. And we're going to choose the annual exports from one of the countries that are in the data set. The data set, the years, the time frame is a yearly, the period is yearly. And also it has many countries, most of the countries in the world. And the year is from 1960 to 2017. And it has many econometric features, GDP, imports, export, population, demographics, etc. So we're going to do a plotting first of the export series against each years against the time, and discuss what we are seeing in the plot. Then we're going to use an ETS model, the one that activates the error as an additive. Okay, so it's an ANN. So it's going to deactivate the errors as an additive model, and it's not going to do the trend or the seasonal. And we're going to plot, we're going to use it to forecast future observations in the series and then plot the forecast. Then we're going to compute the RMSE, which is one of the metrics that we can do to evaluate the model for the training, the training data. Then we're going to use another model from the ETS, but this one is going to activate the trend component. So we, on the original model, we activated the error feature. And now we're going to activate the error and the trend and leave the seasonality as none. And we're going to compare both models, okay, to see which is the one that really gives us a better forecasting tool. And the last is that we have to calculate the prediction interval for the forecast at a 95% interval, but also using the RMS values. Okay, so remember that the RMS is what is called the mean square error. So it comes from the errors between the observations and the fitted values. So what we do is that we square those errors so that we can get all positive values. Then we average it, and the root mean square error, what it does is that average, it squares it. So what we're getting is more or less a standard deviation between the observed and the distance on the average of the errors. And that can be used to calculate a prediction interval. There's going to be some discrepancies, okay, because there's another formula using the variance, but they are, they approximate very well. The RMSE approximates very well that calculation from the variance. Okay, so that's basically the problem. So Federica, if you want to start your solution, go ahead.
Can you see my art?
Yes.
Yeah.
Excellent. I can see it.
Okay, so as Ricardo introduced, this exercise requires you to use the global economy dataset that
Mhm.
you find in the loading the FPP3 library. This, just to do a little recap, this dataset is made of some observations made within different countries, and what we are interested in are the year and the exports. Okay, I've chosen Italy as a country, so filtered
My selection as well.
by Italy. So we can let's run that again just to be sure that, because I reviewed those things a couple of times. So this is Italy. This is just the ad. So we have just the first 6 observations, but in total we have 58 observations in Italy from 1960 to 2017. What we are interested in, as I said, the amount of exports. Okay. So first things is plot the exports series and discuss the main features of the data. So I'll start using the autoplot function from the package on the exports. Percentage of these are exports. Okay. So we can see this is the basically the time series, and it is growing along the time. So it's a clear growing trend. We had like a bit of decrease within the 80s and the 2000s. In particular, I think it's the 90s, around the 90s. So we start going down and then going up again, just the decade within the 19 and the 2000. So there may be quite a few reasons for this, and then we had another trend going down here, which I think is about before the 2010, so like 2008 or something like that, 2007, 2008. But now apparently, so the data are up to 2017. So there is no information about COVID or other things. So it's steady growing from 2010. Okay, so this is the first, so just visualization to see what's happened in Italy with the amount of exports from the 1960 up to the 2017. Now the exercise has to use the exponential smoothing, the simple exponential smoothing. So we take consideration just of the error, as A means additive, So we consider it an additive error, and trend and season are null. Okay, so the very simple one that we saw last week. This time we see with Italy, and if we run this, and we have a quick look at the, this is the model, and then what should I do to see the model result from here? Tidy? No, it's not tidy. Oh, yes, it's tidy. Okay. Here I see my alpha, which is about, so it's very close to the maximum level. Yeah. Yeah. And the level 0, it's 1249. Okay. Let's see if we do a little forecast within 5 years. We can see so that 2018 is the first year after the last observation, and we have a value of 3129. Maybe we could have a quick look at what happened in Italy. In 2017, the value was 3129. And so the next year is steady on the more or less the same value, a little showing a little growth. And then 2019, so the average, it's flat. Okay. So here we have distribution of the normal errors. So we suppose they are normal, behaving normally. And let's have a look at the comparison within the observed data and the fitted data. And so we can see that this is the shift within one period, and this shows the main difference. These are the intervals, so 95 prediction interval, and this is the average value for the years that we have here. So the mean value, the estimated mean value, which is about 31.29. Yeah, and again. Yeah. It says then compute the RMC values for the training data. Okay, so I use a TS table to make sure, because this is a table, but it's if I do class, okay, oops. If I do class, you can see that we have different options. So it's a table, time series, table, data frame. So it gets like confused somehow. Okay. So if I do STS table and then class again, I thought I was so I make sure that it's a TS table, which is that was as well before. Then I stretch a TS table with init option. So I perform stretching windows on a TS keyboard by row. And this, we can see what changes. Basically, now I have, let's go back here. So I had 58 observations. Okay, now I stretch it. And I have 1,666 by 10 observations. Okay. So this function is very interesting. And basically, as I said, stretching windows on a TS keyboard by row. And that said, supply TS keyboard as time gaps. So basically, rolling average. So it stretch the observations to fill the gaps, basically. Because if you run these things without this stretching functions or options, that you have gaps. So it makes sure that so all the observations are full. So I run the exponential smoothing model with the simple one, the very simple one, and a forecast for one period, and then the accuracy to see. It takes a bit because it does both stretching the T-ball and making the model. So I think I did it fast. Maybe because I have the connection. Okay. So here we can see that we have the RMC 1.44. Is that right? Yeah. All good. Yeah.
I'll show you a simpler method to get that number. Okay, Ferica. And it was a slight slight difference. Okay. But there's a way that you can do it a little bit faster. Okay. Yeah, you want me to show you?
Yeah.
Okay. Okay, let me go here. Okay, can you see my screen?
Yeah.
Okay, so yeah, we chose the same country, Italy, right? Okay, so this is the Italy data set. Let me see if I have it here. Okay, then we did the plotting, right? For the time series. One thing that I added, and usually, is I've seen it as a best practice, is to add in the time series to add a lowest, smoother. Okay, so you can actually see if there's a trend, and if the trend is going up, down, or sideways, right? It goes up and down. So here we have a period, right? During the 1980s, we have a period that it really kind of stabilizes and then goes down again and then picks up again. Okay, so it's kind of an inflection point that we have there. Then another thing that I added, to the exercise, which is also I've seen as a best practice, is to do the STL, the season, trend, and level decomposition. Okay, so when we do that, we write out of the out of the table and out of the auto plot, we can see that clearly there's a trend. This is the lows, precisely the lows, smoother that is giving us in the decomposition. But you see that there is no seasonality. Okay, so the seasonality component is not present. That's why when we are modeling, we're using only the error and the trend, components. We're not using the seasonality because the seasonality is not there. Okay, so if you use seasonality, you probably will get an error. So when I did the first model with the ETS ANN, what I do is that I pipe the data set, okay, to the model, and then save it as a fitted, right? As a fitted object. So in the fitted object, and I calling it fit underscore ETS underscore 1 because I know that I'm going to do another model, to differentiate it. I get, I get all the components, in that object, all the components of that object. Then I can do the forecast from that fitted model, right? I can do the forecast, and the forecast is the same, that you got the 31 figure, which is close to the last figure, right? Because we're not trending, right? We're not trending. The only thing that changes here is the variance, okay? The more forecast, the longer the horizon that we get to the forecast, the more uncertainty, those numbers beyond they're going to get. So the variance is going to get a little bit bigger, but the value is going to stay the same because there's no trend. Okay, so for the accuracy, what we have to do is feed the accuracy, pipe the fitted model to the accuracy. And when I do that, I get the accuracy of the training data set, okay, with all the metrics. Since we only want the RMSE, what I did was select, okay? Select, the country, the model, the type, etc., to, get some parameters. And then I get the, I get the RMSE, and the RMSE that I get on the training data, not on the forecast, okay? On the training data is 1.34, okay? But that one, gives you right off the bat, because this is kind of a framework, like the tidy models. This kind of a framework that the authors have, have built in terms of that the commands, the functions for the metrics, for the for the models, they go, they like Legos, that they couple, very well, they join very well. Okay, and using also tidybers. Okay, and then we have the tidy. Okay, I put it, for the parameters, and the parameters are basically the same that you got, which is the alpha 1 and the level at 12.5. Okay, which is basically the same model. Okay, so for the accuracy in the training data, what you have to do is, save that fitted model, okay, in an object, and then pipe it to the accuracy, and it give you, the metric. Okay.
Oh.
Yeah, it's very straightforward. Okay, just like the tidy models, when you have the tidy models, you have the results of the tuning grid. You go and let's say, okay, collect metrics, right? Right off the bat. So this one is basically the same, but instead of collect metrics, you're using accuracy here. Okay. Do you want to continue with the next model?
Yeah.
Okay.
Okay. Can you see my eye? Okay, so as Ricardo said, so to compute the MC value for the training data, we do just the model and then pipe it to the accuracy. And
Correct.
then we find the RMC, which is now 1.33. If I use the stretch table to assure that I don't have any gaps and everything, and then run the model and do a forecast, and then the accuracy, then I will require to add the data inside the accuracy function. I have the RMC for the testing, for the test set, while here it's for the training.
It's just for the training, correct. Yep.
So, and this one is 1.44. Okay. So now what the exercise says, this says, compare the results to those from ETS AAN. So now we are adding the trend component, basically. Okay, so what I did is compare the result to those from I think I should do the same for as I did it before. So if I take this for the training set and then and add an A here. Okay, now I can compare the RMC for the two type of models on the training. I can even like select the type and yeah.
Federica, you should select also the model. Okay, so we can make sure that which RMSE corresponds to the model too. Yeah, that model.
The model. There you go. Yeah. So this is with the forecast, and I added even the dumped export, so the different parameter for the trend. So this might take a bit, well, because there is a for the connection, I think. So anyway. So it says, discuss about the metrics of the two forecasting methods for this data set. And we can, in the meantime, see the plot. And so the results, what are the results of the two methods? And you can see that one is very like optimistic and the other one is a bit like steady. And we explained last week the reason why the first one, so the simple one and the simple exponential smoothing, considering just the error, and here instead there is a the trend component which makes the difference.
Yeah, so the second model, because it's adding the trend element, okay, as additive, is then increasing, right? By period, is increasing that forecast because that's the trend overall. Compared to the one that it didn't have the trend activated as N, then it just stays flat. Okay, and we can see that the RMSE for that additive trend, it's a lower metric, so it's a better model for this type of time series.
Yeah. Okay, just a little mention with the forecast of the three methods. So because here around the other one, the dumped is the best one. Result test the best one. And so the simple one is the lowest. And what else? Here we can see a longer forecasting period within 15 years. Exactly the same. I didn't spend too much time saying that I've just fit and forecast and then auto plot or nothing else, just as the same as before. And then here says calculate a 95 prediction interval for the first forecast of each model using RMC values and assuming normal errors. Let's have a look at what is, this is the first period, so 2018. And we can see that they overlap, basically. The two 95 confidence intervals within the two type of models, they basically overlap to each other. Is that right? Yeah. If we have a look at the forecast for the first period, we can see, as we already saw previously, that this is the normal distribution for the error that we hypothesize, and these are the mean estimations. And to compare, there is this section on the book, which is section this chapter 7. Where is it? I thought I leave it for the show. So this is more information. So about the prediction intervals, you don't see it, what I'm sharing, but I'll share it again. So as you can see, this is on the chapter 5 in the forecasters toolbox, the section 5.5. And it says about the prediction intervals. We went through these things, and a prediction intervals gives an interval within which we expect our response variable to lie within a specified probability. For example, assuming that the distribution of future observation is normal, as we assume the future observation are normal, 95 prediction interval for the H step forecast. Assume this, so it's calculated with this formula. So we consider 1.96, which is the corresponding value of the Z in the normal distribution when we set a 95 prediction interval. This is the sigma. H is the period, so we consider for now one year in advance, so one single period in advance. And so here is a little recap of how to do that. So I'll go back here. Oops. This is not what I wanted to do.
Yeah.
It's my angle. It's gone down the list. Okay.
So Federica, that's the way that the formula that the function is using. When you do the forecast, okay, and then the prediction intervals, it uses that formula. But the question says compare it with using the RMSE, okay?
Yeah.
Which would be an approximation to this, because this is the correct way to do the calculation, right? The RMSE is going to be an approximation, but it's a good one. It's a good approximation, okay? Did you check that using the RMSE?
Okay, what I did it is to use the Hilo
Okay,
function
yeah,
to get the confidence intervals at 95%.
okay,
Yeah, and then I leave that to you.
okay. So let me take it from there. Okay, share screen. Okay. Okay, so we have, right? We have our second model, which is with the error and the trends, right? So I'm going to call that fit underscore ETS underscore 2, right? So we're going to have number 1, which is the error only additive, and then number 2 with error and trend additive, okay? And this is the forecast, and you can see that, it goes really, it follows the trend of the whole thing. So I use the high-low function, to get the original calculation, as this function, the forecast function is using it. Okay, the high-low is part of that. So when we do that, we get this for the first model. We get this range, which is the same range that you got using the high-low. Okay, so we are in the same in the same frequency. Okay, 95%, 95%. Okay, but then what the problem is telling us is, apart from that, use the RMSE to calculate that 95% confidence intervals. And if you look at the formula of the RMSE, it's very similar to the standard deviation. Okay, in other words, the RMSE is the errors to the square, right? The difference between observed and fitted, which is the residual, to the square. Get the average of that sum of the squares, and then do a square root. Okay, so it's very similar to the standard deviation that we're getting from each of the forecasts. So what I did was, because I have this formula for the accuracy, right? Okay, that it gives me the RMSE. So what I did was I pulled the RMSE, the value of the RMSE from that function. I pull it and then store it in what I'm calling RMSE underscore 1, which is the RMSE for that first model. Okay, so this is the value of the RMSE 1.335, which is 1.34, and then I store it here, right? Okay, then what I do is I run the model, get the forecast, and then do a mutate to calculate from the RMSE, calculate the low value confidence and the upper value of that confidence interval. And how I'm going to calculate it? By the mean, right, which is the value, the fitted value, and then adding two RMSEs, okay, which is approximated to the 95% to the 1.96 multiplied by the standard deviation. It's basically doing the same calculation. So when I do that, then I get this interval confidence, which, if we compare it with the high-low, which is the correct way to do it, we get very similar numbers. Okay, the lower number here is 28.633, and here is 28.6. And then 33.95.9, which is 33.96, we get 34. Okay. And the same operation for the next model, right? I pull the RMSE, right? And then calculate the lower and upper value of the confidence interval using two RMSEs. Okay. And we have here 29.0, 28.94, very similar, 34.205, 34.2. So the RMSE is basically a very similar value that we get from the standard deviation of the forecast. In fact, they're very similar, very similar. And then the difference is that instead of multiplying by 1.96, we're multiplying by 2. Okay.
Yeah.
And that will be, that will be basically the difference. Okay.
That's great.
Okay. Got it?
We're done.
Yeah, but it's a nice, way to associate that standard deviation with the RMSE. They're basically the same, the same function. Okay. All righty. So I have my time here is 2:40. Probably your time there is 8:40, right? Okay, so let's talk a little bit about the next chapter. Okay, just a little bit of introduction. On the next chapter, let me get the notes here. Okay. Okay, and the next chapter is one of the most fundamental for forecasting, because as exponential smoothing, ARIMA models are also a traditional model for forecasting time series. Okay, before the the popularization of then machine learning algorithms that they also can do a similar methodology. But before that, before the supercomputers, we got exponential smoothing, and also we got ARIMA. So in this chapter, what we're going to do, we are there's a lot of information here. I'm trying to condense a little bit the information, because there's a lot of math, there's a lot of theory involved. So I'm trying to condense and get the the most important things, so that we can understand what is an ARIMA model. So the first thing that we have to understand for ARIMA is a strong assumption that the time series is stationary. And we're going to talk about that, okay, in this part of the session. And with stationarity, also we have to talk about differencing. And also we're going to define what is that term. Then we start doing exploration on non-seasonal ARIMA, because as you can see, ARIMA is basically autoregression, integration, and moving average. Okay, there are three components, to that methodology. And ARIMA is just an acronym on the words that describe that method. And ARIMA, by definition, is non-seasonal. In other words, you have to convert a seasonal time series to a non-seasonal time series, so that ARIMA then can work on those values. Another strong assumption. Then there's a chapter of estimation, order selection, okay, and we're going to talk about that. Those are the parameters, the order selection, those are the parameters of ARIMA. Then ARIMA modeling in R, forecasting, and also discuss seasonal ARIMA models, because there is an addition to the ARIMA model, which is SARIMA, which combines the ARIMA model with seasonal models. In other words, we don't have to do the differencing for the seasonal. And then at the end, compare ARIMA with ETS, which we already discussed. Okay, so the first thing that we have to understand about ARIMA is that ARIMA is based on what is called the autocorrelation features on the data. So because we have a time series and our observations are in a specific order, one of the assumptions that our Riemann models does is that the last observation that we have is correlated to the ones that preceded that observation. And it's going to be, observed within the time series. So for example, if we have a y, okay, which is the observed value, and we have yt minus 1, yt minus 2, yt minus 3, all of those values are autocorrelated. In other words, they have an correlation factor between each of them. And that's what we call the lags, okay? When you lag it, you are comparing that value with itself, but in a different time period, all right? Okay, so let's talk about stationarity. When we say that a time series is stationary, we are saying basically three things from that time series, okay? The time series doesn't have any trend, okay? So the mean of that time series is constant along the time period, okay, the time range. The second assumption of the stationary time series is that it has constant variance, okay? So for example, if you see the time series and you see the ups and downs, when we talk about constant variance, that means that the amplitude of that, ups and downs is going to be uniform across the time series. So we have constant mean, we have constant variance, okay? And the third component is that there are no long-term predictable patterns. And that is related to the seasonality, okay? So if we have a seasonality, a feature in a time series, it's not going to be stationary, of course, but if the seasonality is repeated in the same periods, that means that the time series is non-stationary. I made this clarification because we study in the first chapters, we studied that the time series can have trend, can have seasonality, and also can have cyclical patterns, okay? So the cyclical patterns are related to the seasonality, but they don't correspond to the same periods, okay? So for example, if we have a time series that goes up and down, but you cannot determine which is the exact period that it goes up and down, that means that that pattern is cyclical. In other words, there's something that is not related to a seasonal component. It's related more to an external factor that doesn't depend on the seasons, okay? So in that sense, a time series that has no trend, that has constant variance, and that has a cyclical pattern that is non-seasonal, it can qualify then as a stationary time series, okay? So let me give you an example. And I took this from a YouTube video, which explains in 5 minutes, it explains this concept, okay? So we see that the first time series to the left that we have here, okay, and maybe I can get a little bit, zoom a little bit here. Let me see. Okay, better there. Okay, so this one, this time series to the left, we can see that apart from the trend, we know that the values through time are increasing. But apart from the trend, we can see that the variance of that time series is very constant, right? Okay, the ups and downs are very uniform across the time. The only thing that changes here is the trend, the increasing. So when you get a period, what we call a window, okay, in the time series, same window within different periods, you'll see that some values are down and some values are up. So this time series, because of the trend, is not stationary. Okay. Then on the one to the left, we get, there's no trend here, right? Okay. If you get a mean across each of these numbers, you see that the mean is going to be very uniform. And also, probably the variance is going to be uniform. Also, you don't see, spikes within the seasonality. What is happening here is that depending on the period, right, the numbers go down. Let's say retail, right? In retail, you know that during the holidays or during Christmas, etc., at the end of the year, usually the retail sales go up, right? And then they peter down again and they go up again on the next year. So that seasonality disqualifies this time series as a stationary time series. So what we're looking is something that doesn't have any trend, something that is, the variance is constant, okay? And then the seasonality, when it's present, it tells us that it's not stationary. If the seasonality is irregular, then it could qualify as stationary. That's one of the, tougher concepts, instead of the seasonal and the cyclical. Seasonal time series are not stationary. Cyclical, depending on the irregularity, they could be stationary. Okay, so to make things interesting, this is from the book, okay, and the author asked us the following question: which of the series, these are 9 time series, which of the series you think is stationary? Which of these series would you pick as a stationary time series?
The last one.
Okay, the last one, the gas production in Australia?
Yeah.
Okay. Okay, let's see. Remember, these are the assumptions. No trend. Okay? That's the first one. If he has a trend, doesn't qualify as stationary. It's non-stationary. Okay?
Okay.
Okay, so this one definitely it has a trend, right? Definitely. Okay. So let's start, discarding. Maybe it's better, to identify the ones that are not stationary, and then the ones that are left will be. Okay. So this one, the Google closing price, okay, for a time period. Definitely there's a trend. Okay. It goes up and down, then goes up, and then goes up again, and all that. That doesn't qualify. Then the strikes in the US, okay, well, it has some spikes, but it goes up again, up and down again. It has trend, not stationary. The same thing as house sales. It goes up and down. It has some seasonality, right? Okay. It could be regular. It could be regular. We don't know, but at least, there's some, there's some seasonality that we can assume that they're regular. So we will say that one probably doesn't qualify. The X price in the US, well, it has a downward trend, doesn't qualify. The pig slaughter in Victoria, right? It goes a little bit up, then down, then up, then down, then up. So it has some trend. There, apart from, there could be some seasonality too. Okay.
Yeah. I think that I thought that was
the pigs. No, the pigs doesn't qualify. No. Remember, for a time series to be stationary, it has to have those 3 components: no trend, constant variance, and no long-term predictable patterns. Okay? And this one, apart from the from the trend and the seasonality, which could be there, it has these spikes that make the variance not uniform. Okay? So the variance also, discarded. Then the links, even though it doesn't have any trend, apparently have some seasonality, right? So probably that won't be non-stationary. Okay, but Let's see what happens when the author explains that one. The beer production, it stays the same, but it has a regular seasonality, so probably won't be. So the only one that we make sure, let's leave links, the links trap, as an outlier. But the one that we can be sure that it, conforms with those three assumptions for the stationarity is this one. The change in the Google price. And it's interesting that what happened is that this one, the closing price, what we're doing here in the change in Google price, what we're doing is an operation that converts this time series from a non-stationary into a stationary. And it's called differencing. In other words, you are going to arithmetically subtract the observation with the preceding observation. Okay, and you're going to get a change in that. Well, when you put in a time series those values of the change in the closing price, that is differencing. And that converts, usually that converts a non-stationary time series into a stationary time series. Okay, so we can be sure that this one is
this one
stationary.
has as well a huge
the huge spike.
Huge spike.
Yeah, but still, if you do a test, a hypothesis test, you will see that it qualifies as stationary, even though you see those spikes. Okay, because they're not that, they're not that regular. Okay.
So a stable trend means isn't it a trend?
That's one component. No trend, constant variance, and long-term predictable patterns. We're going to see this one, the links, because the links, even though we see that there's a seasonal pattern, this seasonal pattern is not constant. Okay. So when it's not constant, in other words, that is cyclical, then that series also could qualify as a stationary, even though it has this up and downs. And I'm going to show you where it says it. Okay. Okay. It's right here. This is the explanation from the authors. Okay, and I'm guessing that the authors know a little bit more than us, in this sense. This says, at first glance, the strong cycles in series G, that links trap in Canada, might appear to make it non-stationary. And that was, my first thought is that it was not stationary because it had these up and downs. Okay. But these cycles are aperiodic. In other words, they don't have a defined period. And what's causing it is that they are caused when the lynx population becomes too large for the available feed, so that they stop breeding and the population falls to low numbers. So that cyclical pattern is caused by something that is not seasonal. Okay. When you're talking about seasonal, you're talking about regular periods, okay? A yearly seasonal, monthly, weekly, daily, etc. So you have a seasonal has a periodicity, right? That it goes up and down, but it goes up and down at regular, intervals. In this case, it doesn't have to do with a season. It has to do with a number of lynx, animals that are in that environment. So when that number goes, grows larger, then they stop breeding. In other words, they stop feeding, they stop breeding to lower the numbers and stabilize again. Then the regeneration of their food source allows their population to grow again, and so on. In the long term, the timing of these cycles is not predictable. Remember, no long-term predictable patterns. So in the lynx time series, we have a stationary time series, okay? Because we have no trend, okay? It just goes up and down, but the mean stays the same. It has constant variance, okay? We don't see the variance, growing larger or smaller through the time. And that apparent seasonality or cycles are aperiodic. In other words, they don't conform to a specific period because it depends on some external factor that is not seasonal. Okay. Okay, so we almost 3 o'clock, and I have to pick up my granddaughter today. Okay, so we'll leave it here, and then we'll start discussing differencing, etc. It's a long chapter, so I'll try to, in 1 hour, try to condense it to get the most. Okay, because if not, we're going to finish this one. Okay, but this is a very important chapter because area models, you're going to see it anywhere in forecasting. In fact, it's used as a baseline usually, like financial smoothing.
Yeah, why don't we split the chapter into sections? So we can do a first part next week, and then the second part the following week. Just if we want to go through all the things, because it's very important as a chapter.
Yeah. Okay. Yeah, I can do that. That there's lots of information here, so yeah, definitely. Okay.
Great.
Okay. Have a great weekend, America, and I'll see you next Friday. Ciao.
Ciao.